Okay, so welcome to the first of two videos on magnetic Rietveld refinement. What I want to do in this first video is go through some of the basics of neutron diffraction and why it is that in a neutron diffraction experiment you can get information about the magnetic structure of a material as well as its nuclear structure. I want to say a little bit about the ideas of symmetry in magnetic structures, because understanding the symmetry of magnetic structures is often one of the big hurdles to starting off in magnetic crystallography. So we'll go through some of those ideas. I'll give you a few warnings about some of the pitfalls that you might encounter when you're doing a magnetic Rietveld analysis, some of the problems that you can get into. And then we'll look at a simple example. We'll look at trying to do a Rietveld refinement of the magnetic structure of lanthanum manganese oxide using a Shubnikov approach to describe its symmetry. And all of the files that you need to go through that example with me are available on the website that's on the screen there. Then what we'll do in the second video is we'll look at the same problem using a different approach for describing the magnetic symmetry. We'll use some of the tools in the software package IsoDistort to set up what's called a symmetry mode refinement of the magnetic structure of the same material. And we'll look at the pros and cons of the two ways of working. So let's start with some of the basics of neutron diffraction. Why is it that in a powder neutron experiment, you can determine the magnetic structure of a material as well as its nuclear structure? Well, the key thing that allows that to happen is one of the major differences between X-ray diffraction and neutron diffraction. The neutron as a particle has got an intrinsic spin and an intrinsic magnetic moment. And that means when a neutron interacts with the material, not only is it scattered by the nuclei of the material, as in a conventional neutron diffraction experiment, it's also potentially scattered by the magnetic moments in the material. So those are the magnetic moments that arise due to unpaired electrons in the material. So in a typical material at high temperature, a material will be paramagnetic, so the direction of its magnetic moments is random. But many materials, when you cool them down, they order magnetically. They either become ferromagnetic, in which case the magnetic moments are parallel, or antiferromagnetic, in which case the magnetic moments are antiparallel. And that ordered array of magnetic moments gives rise to a magnetic neutron diffraction pattern. So it turns out that if you've got unpolarized neutrons, the total scattering that you see, so the total powder diffraction signal that you see, can be separated into two parts. It can be separated into the nuclear component, that's what gives you the regular structural information, and the magnetic component. That's what lets you work out the magnetic structure of the material. And it turns out the magnetic structure factor depends on the angle between the magnetic moment direction in the material and the scattering vector in your experiment. And it's that dependence that lets you work out not just the geometric arrangement of spins, but their orientation in space. So that idea is explored a little bit in the diagram on the right here. If you look at the diagram on the right, I've got my instant neutron beam being scattered by a certain plane in the material in the diffracted neutron beam. Remember, the scattering vector is defined as a vector that bisects the incident beam and the diffracted beam. The blue vector here is representing the direction of the magnetic moments in the material. And it turns out the structure factor expression, this F mag term, contains a sine alpha, which is the sine of the angle between the scattering vector direction and the spin or magnetic moment direction. And it's that dependence that lets you work out the orientation of the magnetic moments in the material. The second thing that we need to remember when we're doing a magnetic neutron diffraction experiment as opposed to a normal nuclear scattering experiment is in magnetic neutron diffraction, there's a form factor term that comes into the intensities. You may know that when you're doing conventional neutron diffraction, you're imagining that the neutrons are scattered by the nuclei of the atoms, and the nuclei of the atoms are sufficiently small that they're point scatterers. And that means you don't get a decrease in intensity as a function of sine theta over lambda, or as a function of 2 theta, in the same way that you would in an X-ray experiment. If you remember, in an X-ray experiment, what's causing the form factor, what's causing the decrease in intensity with 2 theta is X-rays being scattered from different parts of an atom. So if you've got an atomic nucleus here in space, you're imagining an X-ray being scattered by an electron down here and an electron down here. And those scatterings will be slightly out of phase as you go around in 2 theta. And that causes the diffracted intensities to fall off as a function of 2 theta. Well, magnetic neutron diffraction is very similar. What's giving rise to the magnetic moment is the valence electrons in an atom. So we can imagine the scattering as having to occur from different regions of the atom, and that will give rise to a form factor fall off with 2 theta. And in fact, the fall off in intensity as a function of 2 theta is normally more severe for magnetic diffraction even than it is for X-ray diffraction. And that's because the magnetic moments are normally dominated by the valence electrons, and the valence electrons are going to be further away from the nucleus than the other electrons, and that leads to a more rapid fall off in diffracted intensity with sine theta over lambda. So that can mean that the magnetic information in the powder diffraction pattern is typically located at low values of 2 theta or long d-spacing regions of the diffraction pattern if you're doing a time of flight experiment. And you also, the fall off in intensity with sine theta over lambda or inverse d-spacing means that you often have a small number of intense magnetic peaks that you can follow. So you're often limited in terms of the information quality in the magnetic diffraction experiment. Okay, so just to give you an idea of magnetic neutron diffraction, what I've done on this slide here is I've simulated the neutron diffraction pattern, the powder neutron diffraction pattern that you would expect for 2 hypothetical materials. So in both cases, what I've done is I've made a primitive qubit array of metal atoms in grey, and then on each of these metal atoms, I've put a magnetic moment. In the example on the top, I've ordered all the moments ferromagnetically, so you've got a moment pointing up, up, and in the simulation on the bottom, I've created an anti-ferromagnetic arrangement of the moment. So I've got a moment pointing up, a moment down, and a moment pointing up. And in both cases, I've simulated, as I say, the neutron diffraction experiment. And in blue, in each simulation, is the total diffraction that you would see in the experiment. And I've separated out in red the magnetic contribution. Remember I said you could separate out the nuclear contribution and the magnetic contribution, and that's what I've done in these simulations. So what can we notice from these different simulations? Well, I think the first thing that we can notice is that the intensity of magnetic scattering is actually quite significant. In the simulations that I've shown, the amount of magnetic scattering is comparable to the amount of nuclear scattering. Now, I've done these simulations for a typical example. I took the scattering length of iron to do the simulations, which is 9.45 femtometers, and I've assumed an ordered magnetic moment of 4 Bohr magnetons. Now, in a neutron diffraction experiment, you typically see 1 Bohr magneton of magnetic moment for each unpaired electron in the material. So if you had a D4 material with 4 unpaired D electrons, you would expect a magnetic moment of 4 Bohr magnetons. So this value is sensible for a typical transition metal compound in the first row, in the middle of the first row of the periodic table. So magnetic intensities are significant, is the first thing to take away. The second thing you can see, particularly in the simulation of the antiferromagnetic material, you can see very clearly that the magnetic intensity falls off quite strongly with diffraction angle 2 theta. So that's this form factor coming in, meaning that the strong magnetic peaks are at low 2 theta and they get weaker quite quickly as you go up in 2 theta. That's the second thing you can see. And then the third thing you can see is the position of the peaks. If we look at this first example, the ferromagnetic example, the nuclear unit cell giving rise to the nuclear scattering is this simple green cube that I've just highlighted on the screen. And can you see that in this first simulation, the nuclear unit cell in green is the same as the magnetic unit cell, which represents the moment orientations. So because the nuclear unit cell and the magnetic unit cell are the same, you would expect to see the magnetic and the nuclear peaks at the same values of 2 theta. And that's what we see in the simulation. Everywhere where we have a magnetic peak, we also have a nuclear contribution. So the magnetic intensities just sit on top of the nuclear intensities. In the antiferromagnetic case, at the bottom, things are different. The key difference in the antiferromagnetic case is because the magnetic moments are going up, down, the magnetic unit cell is actually twice as large along the A direction as the nuclear cell. So that means we would expect to see peaks at different values of 2 theta for the magnetic diffraction and the nuclear diffraction, just from Bragg's law. And that's what we see experimentally. We see the red magnetic peaks at different 2 theta values to the blue nuclear peaks. And that actually means that when you're studying an antiferromagnetic material, it can be very easy to see magnetic ordering. So when the material is at high temperature and it's paramagnetic, you just see the nuclear peaks. And when you cool it down and it orders antiferromagnetically, you see extra peaks growing in the diffraction pattern. So it can be very easy to see antiferromagnetic order developing in the material. Okay, so those are the ideas that we need to understand about magnetic intensities. I want to come on and think about the symmetry of magnetic materials. As I said at the beginning, understanding the symmetry of magnetic structures is actually quite complicated when you start working in magnetic crystallography. If we just go back to the basics, when we're doing conventional crystallography, what we normally do is we describe the atoms in the asymmetric unit of a material, and then we apply the symmetry operators to the space group to create all of the other atoms in the unit cell. And it's that the atoms in the unit cell that we use to calculate the diffraction pattern. So when we're doing magnetic crystallography, we actually have to think about the effect of the symmetry operations, not just on the atoms in the unit cell, but what they do to the magnetic moments of the atoms in the asymmetric unit. So to do that, we need to understand something about the symmetry properties of magnetic moments. And that's something that's quite confusing the first time you come across it and seems a bit counterintuitive. But it turns out the best way to understand it is to think back to the fundamentals of what gives rise to a magnetic dipole moment in a material. Well, if you go back to classical electromagnetics, what generates a magnetic moment in a classical system is if you have an electric current flowing in a loop of a wire, that will generate a magnetic dipole moment perpendicular to the plane of the loop. And the magnitude of the moment is given by the product of the current that's flowing and the area of the loop. So we can understand magnetic dipole moments, which we normally draw as these little arrows pointing in a certain direction, in terms of circulating currents. What that means is that magnetic dipole moments actually have the symmetry properties of what are called axial vectors. And if you want to understand the symmetry properties of an axial vector, you can think of this little cartoon in the middle of the screen. You can think of an axial vector as a spinning cylinder. So with that idea in mind, let's think about what do symmetry operators do to magnetic moments in a material. So before we look at magnetic moments, let's just think back to a simpler system. Let's just think back to something like an electric dipole in a material, which we can classify as being a polar vector. So here I've got a little sketch in the material of what a mirror plane operator would do to an electric dipole. So this little blue arrow here, which is a polar vector. So what happens to a polar vector when you apply a mirror plane is it's relatively straightforward. Here we've got an arrow pointing up. If you apply a symmetry operation, it's going to move the arrow to the bottom of the mirror plane, and it's going to reverse the direction that the arrow points in. Equally, if you've got a polar vector which is running parallel to the mirror plane, if you apply the mirror operation, it moves that arrow to the bottom, and the direction of the arrow is unchanged. So the mirror operator operates just as you would expect from a common sense point of view. Well, it turns out with magnetic dipoles, things are a little bit more complicated. It turns out if you've got a magnetic dipole, which will represent as a red arrow pointing up, and you apply a mirror plane, what happens is the arrow moves to the other side of the mirror plane, but it stays pointing in the same direction. Equally, if you've got an arrow pointing to the right and you apply a mirror operation, it moves to the bottom of the mirror plane, but instead of pointing to the right, it's now pointing to the left. So that's counterintuitive when you first see it. So why do magnetic dipoles behave in this way? Well, to understand it best, what you should do is think of the magnetic dipole, as I say, as an axial vector. And think of it in terms of this circuit of currents circulating around the arrow that we draw. So if you think about a little circulating current which is moving in an anti-clockwise sense on this arrow above the mirror plane, if you apply the mirror operation, that circulating current will move below the mirror plane, but it still moves in the same direction. So an arrow pointing up becomes an arrow pointing up. Equally, if you have an arrow pointing to the right, we can represent that as a loop of current where the current is coming down towards us. If you apply a mirror operation, it moves the loop to the bottom, but the direction of travel is reverse. So an arrow pointing to the right becomes an arrow pointing to the left. So conventional symmetry operations do what seem to be counterintuitive things to magnetic dipoles. Now, it turns out when we're looking at real magnetic materials, we may need to describe symmetry operations which have got the form on the right here, where the magnetic dipole, the axial vector, does behave like a conventional vector. There may be a symmetry relationship we need to describe where you've got a moment pointing up and it's related by some kind of a mirror to a moment pointing down. Or we might like to relate a moment pointing to the right to another moment pointing to the right. So to do that in magnetic crystallography, we introduce a new symmetry operator, which is called the 1' operator, or the spin reversal operator, or in physics people call it the time reversal operator. So what we do if we want to describe this kind of mirror relationship between a magnetic dipole is you imagine having a magnetic dipole here, you apply a mirror operation, and then you also apply spin reversal, this 1' operator. So after you've mirrored the magnetic dipole moment to below the mirror, you then flip its direction so it changes from pointing up to pointing down. Equally, if you took this arrow here, if you applied a mirror, it would point to the left, and then you flip the spin and point it to the right. So that's called a primed symmetry operation. So it's given the symbol M'. So when we do magnetic crystallography, we talk about standard symmetry elements, which we typically draw in black and a mirror plane M, and prime symmetry elements that we draw in red, which also involve time reversal or spin reversal of the magnetic moment. It's worth thinking a little bit, why is it that physics call this time reversal? To a chemist, it doesn't seem very intuitive. But I think we can understand the time reversal language quite simply. I mean, if you think about taking this spin-up arrow at the top of the mirror plane here, if you were to take that arrow and you were to just move it by a conventional mirror to the bottom of the mirror plane, the moment at the top is traveling in an anti-clockwise direction. If you just moved it by a standard mirror, it would also be moving anti-clockwise below the mirror plane. Now imagine you could take a little movie of that current, the electron moving in an anti-clockwise sense. If you were then to take that movie and play it in reverse time, you would just to play the movie backwards, you would take an electron that's moving anti-clockwise and change it to moving clockwise. So by changing the time axis, by moving from positive time axis to a negative time axis, you're doing a time reversal operation, which actually flips the direction of the spin. So that's why the physics community will call this a time reversal symmetry operator. Okay, these magnetic operators, or operators in magnetic space groups, also have some implications on the different directions that spins can adopt in a material. If we take as an example this red mirror plane, this M' mirror plane on the right of the screen here, imagine that we had an atom which is sitting on the mirror plane, and that atom on the mirror plane tried to have its moment perpendicular to the mirror plane. So if you have a moment perpendicular to a red mirror plane and you apply that mirror symmetry, what it's going to do is it's going to reverse the direction of the magnetic moment. And so that wouldn't be allowed. So essentially what you can say is that if you have an atom sitting on a red mirror plane, it can't have a component of its magnetic moment perpendicular to that plane. If we think about a horizontal moment, if you had a horizontal moment sat on the mirror plane, and you apply that mirror symmetry, it doesn't change the direction of the magnetic moment. So a moment in plane would be allowed on a red symmetry element. And if you think things through, the same kind of ideas hold for a black symmetry element, but they're actually reversed in terms of you can have a perpendicular moment, you can't have a parallel moment. So if we want to understand magnetic symmetry, we have to build together all of the ideas of having black symmetry elements and red symmetry elements, ones which involve time reversal. We have to think about the implications of those on spin directions and which spins are allowed. And as you can imagine, life becomes slightly complicated. Fortunately, there are various tools to help us with that. When we're doing conventional crystallography, if we want to understand normal space group symmetry, we would use international tables, and that tells us information about conventional space groups. There's an equivalent set of tables for magnetic space groups, There's a nice paper on them, and they're developed in this paper on the right by Daniel Litvin. So the international tables, the equivalent of international tables with magnetic space groups, are in the supplementary information to that paper, or they're available directly for download on the website by my laser pointer on the screen. But if you look at the magnetic space group table, you'll see information in them which looks a little bit like the information we're familiar with from regular international tables. I've just taken some pictures from Daniel's publications for one space group. It's a space group that's got the label or the space group name P2B M prime M A prime. We won't worry too much about what that symbol means. But what you find for each space group is pictures like the pictures on the screen. In the center of the screen, where my laser pointer is at the moment, what you have is a diagram showing where the different symmetry elements are in the unit cell of a material. And the only difference to international tables is that some of the symmetry elements are colored black and some of them are colored red. The ones that are colored red are the ones that also involve time reversal or spin reversal, which flips the direction of a magnetic moment. The picture on the left of the screen here shows what happens to an atom on a general position in that magnetic space group when you apply the different symmetry operations. So when my mouse is now shows an atom at a certain position in the unit cell, if it's drawn in red, it actually means it's slightly closer to you than the plane of the paper. If it's drawn in blue, it's slightly further away from you than the plane of the paper. There's a little arrow drawn which shows you the direction of the magnetic moment in the material. If it's got a plus on it, it means it's pointing slightly towards you. If it's got a minus on it, it means it's pointing slightly away from you. So you can see what happens to magnetic moments on different sites in the unit cell. It turns out things are slightly more complicated than that in that in certain space groups, this is actually what's called a type 4 magnetic space group. And in the type 4 magnetic space group, one of the translational symmetry operators is actually primed. And that's drawn in the, represented in the little cell vectors in the top left of the screen. Can you see that the y-axis here is drawn in red? And that, what that means is that there's time reversal along the y-axis. So the unit cell of the material is actually twice as large as the unit cell that's drawn here along the b direction. And you would actually have a copy of this part of the unit cell translated along in the b direction. And the copy of that unit cell has all of the symmetry operators primed relative to the portion that's drawn in the diagram. And so that's telling that essentially you would have antiferromagnetic arrangements between one part of the unit cell and the next part of the unit cell over. You can see some hints that that's happening in this space group name here. You see that where it says P sub 2b, that's telling you that the b-axis is doubled relative to the paramagnetic space group that this is derived from. Okay, so there are these pictures in the space group tables. What you also have at the bottom of the screen here is you have information just like you would in conventional international tables about what happens to atoms on specific sites in the material. So there's a list of the different Wyckoff sites. I've just shown some of them here. So for example, there's a Wyckoff site which is labeled K and has a site multiplicity of 8. So for every atom in the asymmetric unit, you produce a further 7 in the unit cell. The point group symmetry of that specific site is given here. This is an M prime site. And then you have some numbers which describe what happens to an atom in a position XYZ when you apply different symmetry operations. So that's just like conventional international tables. What you have in addition in these square brackets is the restrictions on the moment direction. So remember we said on the previous slide that if you have a red magnetic plane, you can't have a magnetic moment perpendicular to that plane. It's not allowed by symmetry. Well, what we've got here is we've got a site symmetry of M prime. That means we've got a red mirror plane in the x-axis. So that should tell us we can't have an x component of the magnetic moment. We can see that in the allowed directions for the magnetic moment. So on each of the sites, the atom has to be on the magnetic moment can have components 0 VW, 0 V minus W, 0 V minus W, and 0 VW. But the x component is always 0 on each of these sites, which means that the moment has to lie in the plane. So all of that information is stored for you in the crystallographic tables, which, as I say, you can download from this site. So the combination of all these things, having black mirror planes and red mirror planes and restrictions on the magnetic moments, means that magnetic symmetry is more complicated than regular space group symmetry. As you know, there are a total of 230 regular space groups. There are a total of 1,651 of these magnetic space groups, or two-color space groups, or Shubnikov space groups. If you're interested in the history of how they were developed, there's a nice publication by Andrew Wills from 2017, which talks about some of the ideas, some of the ways in which these symmetry ideas were developed. If you want some tools for exploring symmetry, we'll look at those in the next tutorial a little bit, but there are these two websites on the right which contain lots of useful information about magnetic symmetry and how you can explore it. It turns out that there are actually lots of different subtleties and lots of conventions in terms of how the different magnetic space groups are labeled, how they're described. Topas currently uses what's called the BNS nomenclature when it's describing its space groups. So each of the magnetic space groups is given a symbol that looks something like this one here, C sub A MMA. They're also given a serial number. When we talk to Topas, when we interact with Topas, what we'll actually be using in this is this BNS serial number for telling Topas the magnetic space group. All that information is stored for Topas in a file called Shubnikov groups.txt, and we'll look at that when we go through the example. Hopefully in the future things will be a little bit simpler. There was a paper in 2022 by Branton Campbell and colleagues which describes a new system for labeling magnetic space groups, which is hopefully a little bit more logical and a little bit easier to understand than the historic convention. So I think in the future that will hopefully become the standard that people use. Good, so enough about symmetry. Before we come on to the example, just a couple of little warnings about some of the ambiguities that are present when you do magnetic powder diffraction experiments. One of the things that we'll know about powder diffraction already, even if you're just doing conventional crystallography, is that peak overlaps can lead to a loss of information in the powder diffraction pattern, and that can make conventional structural refinements difficult to do. In the case of magnetism, it can make things even more difficult. If, for example, you think about a cubic material, in any cubic material, the 100 reflection and the 010 reflection and the 001 reflection will always overlap with each other perfectly. And it turns out that when you're doing magnetic neutron diffraction, that means that you lose information about the direction of the magnetic moment in a material. So for a cubic system, a cubic collinear magnetic structure, all you can determine is the magnitude of the magnetic moment. You can't say anything from a powder diffraction pattern about the orientation of the moment. Similarly, if you've got, for example, a tetragonal material or a rhombohedral or a hexagonal material with a unique axis, something like a tetragonal material where the c-axis is unique, you can get information on the moment direction relative to the c-axis, but you can't get any information on the moment orientation in the AB plane. You need to be aware of some of these ambiguities. They're discussed in the publication on the right here. And then the final thing just to keep in mind is that there can actually be some structural ambiguities in magnetic diffraction, which the first time you see them might seem surprising. Just to give you an example of that, I've simulated the magnetic diffraction pattern, or in fact the total diffraction pattern, magnetic and nuclear, for two different hypothetical structures. In the structure on the top, I've taken a series of metal atoms. I used iron again, just as in the previous example. And in the top simulation, I've put the moments so that the moments are ferromagnetically coupled between the first two atoms and then antiferromagnetically coupled to the next atom. So the moments go up, up, down, down, up, up, down, down. And in the second simulation, I've put a moment on the first atom up, no moment on the second atom, and I've put a moment down on the third atom along. And I've made the moments in the second simulation larger than in the first by a factor of the square root of 2. It turns out that the diffraction patterns, the neutron diffraction patterns for those two materials are absolutely identical. Even though these magnetic structures look very different to each other, there's no way of distinguishing them by powder neutron diffraction. So you just need to be aware that sometimes there are some ambiguities in the models that you develop. So with that said, let's come on and start to look at the example that we're going to look at in this tutorial. And this is one that doesn't have any of these nasty ambiguities. So the example we're going to look at is the magnetic structure of lanthanum manganese oxide. So this is a perovskite material that's part of the family of GMR materials, giant magnetoresistive materials. It's a very important perovskite material. So this is the structure of lanthanum manganese oxide on the left of the screen. As with any perovskite, it contains octahedral transition metal. So this is a manganese surrounded by 6 oxygen atoms, and each octahedron shares its corners with another octahedron to give you an infinite network of corner-sharing octahedra, and then the lanthanum atoms sit in between the octahedral framework. Okay, so the nuclear structure of this material is high-temperature structure in paramagnetic form. It's an orthorhombic distortion of the perovskite structure. It's got space group symmetry PNMA. When you cool the material, it orders antiferromagnetically, and the magnetic space group becomes PN prime M A prime. So the magnetic structure of the material is interesting. What you find in the material is it has ordered moments. The moments are around 4 Bohr magnetons. This is a manganese 3+ material, manganese 3+, 4 unpaired d electrons. For each unpaired d electron, you'd expect a magnetic moment of around 1 Bohr magnetons. It's a 4 Bohr magneton moment. It turns out in this material, the magnetic moments order antiferromagnetically along the b-axis, but they order ferromagnetically in the AC plane. So that's the magnetic structure that we'll try to determine. If you're interested in why it adopts that particular magnetic structure, we're not going to go through it in this tutorial, but if you're interested in the physics behind why it adopts that particular magnetic structure, you could look at the textbook that's on the screen on the right here, Solid State Materials Chemistry. That's a book that I co-authored with Pat Woodward, Pavel Karen and Tom Vogt. And chapter 9 on there is all about magnetic ordering in materials, and it goes through the reasons why this material has this particular magnetic structure. But let's stop the slides for now, and then let's just switch and try and actually work out the magnetic structure of this material. To do that, we're going to use some actually simulated neutron diffraction data, but it's simulated data that's based on the experimental model that was reported by Musar et al. So let's switch to the desktop and try and do a magnetic Rietveld refinement. Okay, so here we are in my desktop, and let's get ourselves ready to do a magnetic Rietveld refinement. Just before we do that, there are 2 files that we could look at, which Topas reads when it's doing magnetic work. The first is this file called Shubnikov groups.txt, which I mentioned in the video. It basically contains the space group information for all 1651 of the Shubnikov groups. So the one that we're going to be working with is space group 62.448. So if we look through the file, we can see the entry for that particular space group. Here's its space group name, P, N prime, M, A prime, and here are the various symmetry operators. So we've got the X, Y, Z symmetry operators, and then the time reversal operator at the end. So that's not a file that you'll ever need to change, but it's sitting there in your Topas directory if you want to look at it. The other file that you may sometimes need to change is the file that contains the form factors, the magnetic scattering factors. Remember I said that in the neutron experiment there's a form factor like an X-ray experiment. So there's a file in your Topas directory which contains the information that Topas uses to calculate the scattering factors. The equations that it uses are written at the top, and then the coefficients that go into those equations are listed for all of the common elements. So occasionally you'll find that you'll be working with an element that's not in that file. So if that's the case, you can add extra information to it. I think at the bottom of this file somewhere, here, I was doing some work on an osmium compound, so I had to add the scattering factor information for osmium. So I got that by fitting some data in the literature. If you do ever need to do that, just be a little bit careful and make sure that you follow the Topas way of describing these form factors. So it uses 7 coefficients. And there are actually 2 coefficients in the equations that used to have to be 0. There are some 9 parameter descriptions of magnetic scattering factors in the literature, so make sure you don't put the wrong values into these columns or all of your calculations will be wrong. Okay, so let's put that file away and let's try and do a very simple Rietveld refinement. So as I said, the data set that we're going to be working with, it's a simulated data set on LA-MNO3. So you can download from the web a data file, which is just in XY format, 2 theta and intensity. And you can download a nuclear CIF file, which contains the nuclear structure for LA-MNO3. Okay, so what we can do now is just go through the standard Topas menus to set up a Rietveld refinement for LA-MNO3. So we'll do this reasonably quickly because we've gone through this in previous tutorials. So what we need to do is a simple Rietveld refinement. So let me pull down that menu. I need to select my data file, which is this mag.la-mno3.xy. So let me select that and open it. And the instrument that we need to use is a constant wavelength neutron instrument, and the wavelength is 1.54 angstroms, so I can select that. We don't need to refine the 0 point because it's simulated data. We can read in the CIF file, so the nuclear CIF file is here, LAMNO3 pnma.cif, and that's all we should need to do a simple Rietveld refinement. So let's put away the X insert menus. We can send this file to Topas, give it a sensible file name. If we switch to Topas and then run a Rietveld refinement, see what we see, we get this fit in the background here. If we look at this fit, obviously it's a reasonable fit. If we look at high angle, we're getting a nice fit to the diffraction pattern. But if we're looking at low angle, there are several peaks which have got 0 calculated intensity. And these, of course, are the anti-ferromagnetic ordering peaks, so the magnetic peaks that we're trying to fit. So let's go back to JEdit and just in general set up a couple more parameters that might be useful before we introduce magnetism. I know that in this example, all the atoms will have the same temperature factor because that's how I simulated the data. So let me just put a single temperature factor on all the atoms. I happen to know that we can use a simpler peak shape. I simulated the data just as if we had a Lorentzian size broadening on the sample. So we can have a simple peak shape description to describe the diffraction data. And in a general case, you might need to refine the atomic coordinates in your nuclear model. And so in this particular material, there are actually 7 coordinates that are free to refine, 7 degrees of structural freedom, which are 2 parameters on the lanthanum, 2 parameters on oxygen 1, and all 3 XYZ parameters on oxygen 2. So let's turn those on and try and refine those, but probably it's not going to change our fit in any significant way. And in reality, this might be a silly thing to do. But anyway, let's do the refinement and look at the results of the refinement. And we've got an R factor of 14.27%. Okay, so let's go back to our input file and try and introduce the magnetic model. And just so I don't make any mistakes when I'm typing, I've got a little cheat file that I can open alongside just to remind myself of all of the commands. So the first thing that we need to do is, because we're doing a magnetic refinement, we are going to need to tell Topas the magnetic space group. And if you remember, the magnetic space group is 62.448. So that's the magnetic space group that we need to use. It's not absolutely vital, but in a minute, it's going to be useful if we give the scale factor a parameter name when we do the refinement. So I'm going to give the scale factor a parameter name, scale underscore nuclear. And then the other thing I need to do is make one of the atoms magnetic. So the only atom that's likely to be magnetic in this case is the manganese site. So if I insert an extra line, this line defines the projection of the magnetic moment along the x-axis, along the y-axis, and along the z-axis. So I've started off with 0 moment along the x, the y, and the z-axis. Just to get myself started, to make sure I don't get into a false minimum, I'm going to put the component along x, the component along y, the component along z to just be small positive numbers. Now I've turned all of these parameters on so that they're going to refine. And in general, with magnetic structures, Topas is clever enough to know which parameters you are allowed to refine by symmetry and which you're not allowed to refine by symmetry. So if you try and refine something that you're not meant to, you'll get a warning. If I've got things right, that should be everything that we need to do a simple magnetic refinement. So if we send that file back to Topas and just click the step button, my R factor is 14.8. Let's do 1 cycle, 2 cycles, 3 cycles. And can you see that the magnetic peaks are now starting to fit really quite nicely? So let's refine that onto convergence. And you'll see that I've got an R factor here of 3.92%. Okay, so that's our simple refinement done. We should probably look at the results of the refinement. There are a few ways you could do that. One thing we could do in Topas itself is we could just look at the structure. So if I do view _ structure, I'll be able to see our structural model and actually our magnetic model at the same time. So if I run Topas again, here's the refined structural model popping up. If I put the polyhedra on, you can see that that's a nice perovskite structure, tilted, corner-shared octahedra. If I turn the polyhedra off and I draw the atoms, I get rid of the atoms, you can hopefully see that the magnetic moments have been refined here and they're plotted on the picture. So we can see that this moment and this moment are parallel to each other. We've got ferromagnetic layers in the AC plane, but along the B axis, this moment and this moment are anti-parallel. So we can view the magnetic structure in Topas. What you probably want to do in general is look at the magnetic structure in another viewing program. And you may have watched the video on SIF files. So there's a video going through the beautiful macros that Matthew Rolls has written for us to make nice structural SIF files. It turns out those same macros will also make magnetic SIF files. So we can output a SIF file at the end of this refinement as well. And that will let us look at the structure in another program. So we're going to output a file called magnetic.sif. So if I run Topas again, I should get a file called magnetic.sif written into my directory. And so here it is. If I open magnetic.sif, it's got all the normal SIF information in there, but it's also got information, for example, on the magnetic space group operators, and it should have information about the atomic moments are written in there. So that's a file that you should be able to look at in other software. I tend to use Vesta, so we can just drag that SIF file into Vesta and we can see the magnetic structure in Vesta. I opened it up previously, and here's the picture, the same picture, but just colored as it was in the slide. So again, we can see these nice ferromagnetic moments in plane and then anti-ferromagnetic moments ordering between the planes. Good, so that's all we need to do for a standard magnetic Rietveld refinement. So let me go back to JEdit. I mentioned in the slides that it's possible to actually separate out the magnetic and the nuclear parts of the scattering. And it turns out that in a Topas input file, it can often be very convenient to separate the magnetic and nuclear contributions to the diffraction pattern, because it means that we can visualize the magnetic scattering separately. So let's just change our file to do that. In Topas language, it's called mag-only for mag sites. So let's save this file as a new file name, and I'll just call it mag-only.inp. Okay, and so we just need to modify our file slightly to calculate the nuclear and the magnetic scattering separately. And just for safety, I'm just going to delete the information that's outputting the SIF file. And then what we need to do in Topas is we need to input a second structural file to describe the magnetic only phase. So what I'm going to do is I'm going to take my structural model and I'm going to copy it a second time in my file. And if I go back to the first structure, the first structure is going to describe just the nuclear scattering. So I'll call that LAMNO3_nuclear. Because this is going to be a conventional non-magnetic neutron refinement, I need to change the space group back from the magnetic space group description back to its original normal crystallographic space group, which is PNMA, and I need to get rid of the magnetic scattering from the manganese site. So that's now back to a normal Rietveld refinement. And then the second structural phase I'm going to call LAMNO3 underscore magnetic. Let's get rid of the information about the SIF output because we're not going to do that. This is now a magnetic model, so I need to keep the magnetic space group in there. But in this case, what I want to do is that I only want to calculate the magnetic part of the diffraction pattern. So the Topas keyword for doing that is this keyword mag only for mag sites. So that says to Topas, only consider the magnetic scattering from the magnetic site. So in this particular model, I don't need the lanthanum atom because it's not magnetic. I don't need the oxygen atom because it's not magnetic. And I don't need oxygen 2 because it's not magnetic. Now, the scale factor, in this particular case, the unit cell volume of the magnetic structure and the non-magnetic structure are identical. So I could actually equate the scale factors between the two. In general, though, you need to equate the scale factors according to the volume of the nuclear and the magnetic unit cells. And so what we'll need to do is we'll need to give the magnetic phase, we'll set this up as if we needed to do this. We'll give the magnetic phase scale factor a name scale underscore magnetic. We'll pull out a parameter which is called the volume of the magnetic phase. So let's have a parameter called defining the volume of the magnetic phase. In my normal structural phase, let me have a parameter for the nuclear phase, which I will describe with a parameter name as well. So let me take that line and put it into my nuclear phase. So this is going to be the volume of the nuclear phase. So we've got the scale of the nuclear phase defined, the volume of the nuclear phase defined, the scale of the magnetic phase, the volume of the magnetic phase. Now, in fact, the scale of the magnetic phase we should describe by a simple equation. It depends on the square of the volume ratio between the magnetic and the nuclear phase. So let's put that in as an equation. And it's an equation, so it needs a semicolon at the end. And so if I've remembered everything, that should have us set up perfectly to do a two-phase refinement, one nuclear phase, one magnetic phase. So let me send that to Topas and just run things, and hopefully I haven't made any mistakes. Let me click a go button, and you can see now that I've got exactly the same R factor as previously, but now in the calculation, Topas is showing me two separate phases. The nuclear phase, so we can highlight the nuclear phase in blue and have a look at its diffraction pattern. And in green is the magnetic contribution to the diffraction pattern. So just as when we were looking at things in the slides, you can see that the magnetic only peaks are strong at low angle, but then they fall away rapidly at high angle. So in this particular case, beyond about 50 degrees 2 theta, there's very little contribution from the magnetic pattern. Okay, so hopefully that gives you an idea of two ways to do a magnetic Rietveld refinement in Topas. One using Shubnikov groups where you describe the magnetism and the nuclear diffraction from a single phase, and one where you separate out the nuclear scattering and the magnetic scattering. And in the next video, we'll look at some different ways of understanding magnetic symmetry in materials. So we'll do what's called a symmetry mode analysis of the same data, and you'll learn some new tricks about symmetry distortion modes and different ways of understanding magnetic symmetry. So see you in that next video. Bye for now.